Hi, everybody. Welcome to class today. Today, as I promised, we have a really surprising, kind of interesting application of these rules yesterday, these determinant rules that didn't seem particularly important about what happens when you change a matrix. How does its determinant change accordingly? It's going to lead us to a very efficient way to solve systems of equations. And that includes even like 3x3 and 4x4 systems of equations. To get us started with it, though, I would like you to treat A, B, C, D, E, and F as constants. And what would happen if you did just regular, elimination method to isolate the X term, to eliminate the Y term? What would X be in terms of A, B, C, D, E, and F? So everyone take a few minutes to ponder that. I'm going to pause the recording and you could chat about what you come up with as you get it. Okay, I see some answers popping up in the chat. And yes, you do get, if you do the process, you do get EC or CE minus BF over AE minus BD. Now, if you look carefully at this, what is this CE minus BF and AE minus BD? What do those remind you of? They look like a discriminant, determinant. Now I got myself used. Determinant of a 2x2 matrix, and they are actually. Take a look here. I went one step further. That CE minus BF is the determinant of the matrix CBFE, and the AEBD. AE minus BD, sorry, is the determinant of ABDE. Well, that's actually going to lead us to a formula, although it's not going to be clear how to generalize this yet. But if we call the variable D, if we call capital D the determinant of the matrix formed by the four coefficients, and we call D with a little subscript of X, that's going to be the determinant of a 2x2 matrix also. But look at this CFBE. What it is, it's the same thing as this bottom one, except the numbers in the first column have been replaced with the numbers after the equal sign. And while we're at it, a third number can be calculated. I'll call it dy. And that's going to be the same as this, except in this case, the second column is going to be replaced with the stuff after the equal sign. So we've got the D, which is determinant of the coefficient matrix. D subscript X is the determinant of the coefficient matrix, but the first column is replaced with the stuff after the equal sign. And dy is the determinant of the coefficient matrix with the second column replaced with the things after the equal sign. And if you do all that, X is going to be dx over d, and y is going to be dy over d. And with that, we can answer a 2x2 system of equations. And I don't know that this is necessarily faster than elimination method, but I know for a 3x3, it's going to be really useful. So here, the three determinants, and here I wrote DET. That could also be written as like almost like an absolute value. Anyway, would you go ahead? You can see that the 3 minus 2, 6, 1 are the four coefficients. And the TX is the same matrix except the 4, 13 replace column 1. And the DY is the same as the original except the second column is replaced with the 4, 13. Would you go ahead and work out all three of these determinants? And in the denominator of both of the answers is going to go this first thing. And the numerators are going to be this and this. Okay, so does everyone take a minute to work those out? Okay, so what should the answers be for X and Y in this case? Go ahead and type it into the chat. That's right. X equals 2 and Y equals 1. So dx over x is 30 over 15 equals 2. And dy over d, is 15 over 15. Maybe this is the fastest way to do 2x2. It is pretty fast way to solve it. But at this point, it's just sort of mysterious. I mean, yes, we could derive it this way by like just noticing, oh, it does become a fraction with things that look like 2x2 determinants. But that's not really explaining, why that works or if it can be generalized. The proof is coming at the end of the class. But what I want to show you is that, and this, I'm going to put you into groups for this one now. So, and I wonder if there is someone waiting to come in. So here we have a 3x3 system of equations. And this Cramer's rule that it's called works for 3x3 systems of equations also. There's four determinants that need to be formed. D, dx, dy, and dz. Now I'm going to put you into groups, and I'm going to have each group work on, everyone's going to have to do the D, the 3x3 determinant of the coefficient matrix. Everyone's going to have to do that. But the groups will only have to either find X, Y, or Z. So let's see how many people I have. I have 23 people. It's going to be 6 groups. So if you're in groups 1 and 4, you're going to work out dx. If you're in groups 2 and 5, you're going to work out dy. If you're in groups 3 or 6, you're going to work out dz. Every group's going to work out d. And then depending on which group you're in, you'll either get dy, dx, dy, dz. I'm just clear, when I put you into groups, I believe the equation disappears. So just make sure over the next minute that you write down or take a picture or do whatever you need, because I believe that you won't have access to the picture in a few seconds. Okay, I'm going to put you into the groups now for about 10 minutes. You're going to work out the two 3x3 determinants. You know, you expand along a row or a column. There's no zeros, so, but there are a lot of ones, so it shouldn't be too hard to do that. Okay, breakout rooms starting, and they will be going on for 10 minutes. Assign participants into 6 rooms, and I come and visit the rooms. Okay, so let me pause the recording. Okay, recording again. So yes, D was 7 and dx was 7. So x was dx over x, which is 1. For y, dy was 14. 14 over 7 is 2. And finally, people in groups 3 or 6, what was your 3x3 determinant? dz became 21. Divided by 7 is 3. I see you got negative 14 in that other group. Well, let's take a look. I have, here's the work for it, or actually, no, there is not work there for it. But what row did you expand on if you got negative 14? Did you, or column? You did row 1 or column 1, and you got negative 14. Let me take a look at that. So if you do row 1, it's 3, 15, 4, minus 12, minus 3, minus 2, that's minus 1, 4, 1, minus 3, plus negative 1, minus 1, 15, 1, minus 12. This is minus 45 plus 48 is 3, so that became 9. This became 3 minus 4 is minus 1, so that becomes plus 2. And this becomes minus 1, 12 minus 15 is negative 3, so that ends up becoming plus 3. So 9 plus 2 plus 3 is 14. Oh, if you switch the order, then yes, like one of the rules from yesterday, we would get negation. So that's the main lesson: how to solve what Cramer's rule is. But the big question is, you know, why does this work? It's pretty bizarre, this method of the coefficient matrix. One way to do this, which is not how you would want to, would be to take a 3x3 system of equations, you know, ax plus by plus cz plus d, and do an entire thing and just verify that if you did the 3x3 system, you would get those determinants. But that would probably take a good hour to do. And that would only show that it was true for the 3x3 case. It wouldn't show that it's true for if we do this with 4x4 or 5x5 or anything like that. So here comes the very clever proof of Cramer's rule, which will only take 5 or 10 minutes, and it proves it really convincingly. So here's a 3x3 system, kind of generic. I just call the coefficients A1, B1, C1, A2, B2, C2, A3, B3, C3, and I call the things after the equal sign D1, D2, and D3. So I haven't done anything yet. I'm just calling the equation this. Now, let's examine the whole, I'm just going to do it for x. So I want to examine what d and dx kind of look like. So here's d. D is just what we would expect. And I'm not going to actually work it out. I'm going to leave it just like that. So this is kind of neat. So D looks like this. And believe it or not, I am not going to start expanding D and putting all these things together. I'm not going to need to. This proof of Cramer's rule is like probably the slickest proof that you'll get in the semester or in the year even. Okay, it's also true that dx is the determinant of the 3 by 3 matrix, which is the coefficient matrix, except the A1, A2, A3 is instead replaced with D1, D2, and D3. Now, why x should equal dx over x is mysterious right now. We have this, and we have this. But here comes the slick proof. Well, since these D1s and D2s and D3s are part of these equations, so D1 equals this thing. So I can replace D1, D2, and D3 in this dx matrix. And this is still a 3 by 3. It's just that I have like a pretty involved elements here. Now this is looking like a pretty big mouthful. And you might suspect that you're going to have to, at some point, start expanding, taking the actual determinant of these 3 by 3 but we're not. That's what's so great about this proof. It's actually almost over. How in the world is x going to pop out of all this? Well, here's what we have. And I'm going to do a column operation on this tx thing. I'm going to do negative y column 2 plus column 1 into column 1. What is that going to accomplish? And here's this sort of, what if I do negative y column 2 plus column 1? What is that going to accomplish? Here's column 2. If I do negative y column 2 plus column 1, what's going to happen? Someone put that into the comments, please. Yes, it's going to accomplish getting rid of those B1y, B2y. And what's it going to do to the determinant? Because when I do that, it surely changes the determinant, or does it? Does doing that change the value of the determinant or not? And why not? Is that Riley? That's right. Actually, wait, it's not that row operations don't. Most row operations 1 and 2 do affect the determinant, but rule 3, the one where you multiply a row and add it to the other one, doesn't affect the determinant. And what if I then, before I start copying, what if I then do minus z C3 plus C1 into column 1? What's that going to accomplish? That's right. It's going to remove all these C's. And what effect will that have on this dx determinant? That's right, it has no effect. So now we have this. And believe it or not, we are one step away from completion. Think about this now. Where can we go from here? There's just one more thing to write, and this entire proof is done. But what is it? Maybe you could write two things. Yeah, Okay, yeah, that's right. When you take out the x, we get to do this. We get to pull out the x, because remember, what was that? Was that rule number 1 from yesterday, or rule number 2? I can't, it was rule 2, the multiplying a row or a column by a constant or by something multiplies the determinant by that. And now what? Where have I seen this before? That's right. Asher says it's the matrix for D. Remember D? D from here? No, D from here? That's not D. Here it is. So the final step is that. Dx is equal to x. D subscript x is equal to x times the D determinant. And then if you divide both sides by D, you get that. See, that's a proof that comes out of nowhere. You wouldn't expect, you'd expect to have to do some kind of expanding or something, but that's why I mentioned yesterday that there would be a good payoff on this. The rules from yesterday would lead to this Cramer's rule. Okay, someone asked, what if D was 0? Yeah, so when D becomes 0, you've got 2 rows that are the same, and that happens, there'll be either infinite solutions or no solutions. That's a great question. If this thing would end up being undefined, it will happen in the case where there's infinite solutions or no solutions. Okay, so that is what I wanted to show you today. We've now done Cramer's rule, and we're done with the required matrices, all the topics for matrices that are required. On Tuesday and on Wednesday and on Thursday next week, I'm going to do some extra things with matrices, applications that you might find to be kind of fun and interesting. And then we finish off with about 4 days of this topic called limits. Now, I changed the due date of the homework from yesterday, and also test number 5. I accidentally made it due on Monday, which is Memorial Day. I changed those to Tuesday. Okay, does anyone have any questions about Cramer's rule? I threw into the homework 2 or 3 delta math questions, 2 with 2x2s doing Cramer's rule, and 1 with a 3x3.